Hi, welcome back to educator.com. Today we're going to talk about understanding exponents. At this point, we're quite used to using exponents. We've seen them a bunch, and we just did them a whole lot when we were working with polynomials. So we know that an exponent is just a shorthand way to express repeated multiplication. For example, if we had 3 to the 7th, that would be a way of just saying 3 times 3 times 3 times 3 times 3 times 3 times 3. That's 3 multiplied by itself 7 times. So the number that we multiply, the number of times it multiplies, is what the exponent is. That's what it represents. X squared is x times x. X cubed is x times x times x. 3x's. X to the 4th would be 4x's multiplied together, etc. So that's the idea of exponentiation. It's clear how this process works when the exponents are positive integers. It's just multiplied by itself that many times. But what if we wanted to expand to any real number? What if we wanted to be able to exponentiate to any real number at all? If we wanted to know things like 3 to the 0, 3 to the 7/8, 3 to the -5, or 3 to the root 2, how can we deal with that? So this lesson will show us how to work with any kind of exponent, any real number. You may have seen rules for this stuff in a previous math class, but we're also going to work through an understanding of why these rules are true. Even if you remember what the rules are for what 3 to the 0 is, for instance, you might not have a good grasp of why 3 to the 0 is what it is. And so this lesson, we're actually going to see how we build these rules, where they come from, why we can trust in them, and also how we can make them ourselves if we ever forget the rules. If we forget the long summary list of all the rules for exponents, we'll be able to just go back to our workshop and work it out even in the middle of an exam. It won't take that long for us to figure out if we have a sense of how we get these things. All right, at heart, exponentiation is this idea of repeated multiplication. That is the basic fundamental idea. By definition, for any number x and any positive integer a, x to the a is equal to x multiplied by itself a times. This is the key idea behind all of our coming rules for exponents. If we start with this idea and we just hold it as a fundamental truth and see all the places that it can take us, we'll be able to get all these other cool rules that will explain how it will work for any real number. So we take this idea, we say, we believe in this, and then we move forward and we try to figure out what else has to be true if this idea right here is always going to work out. Let's see. First thing we can figure out, with this idea in mind, we can consider what happens when we multiply. That should be multiply, not multiple. Multiply some x to the a and x to the b. By definition, if we have x to the a times x to the b, then that means we've got x to the a, so we have x multiplied by itself a times, and x to the b, x multiplied by itself b times. Now, that means we've got some number of x's there, some number of x's there, so we've got a x's on one side, b x's on the other side. So how many is it together? Well, let's say if I had a pile of 5 rocks over here and I had a pile of 12 rocks over here, then in total I would have 17 rocks. If I had 3 rocks here and 4 rocks here, then I'd have 7 rocks total. So if we've got a rocks and b rocks here, then together that's going to be a plus b rocks, or in this case, x's. So we put them together and we see that we've got a plus b many x's showing up. Thus, x to the a times x to the b equals x to the a plus b. So this is another really fundamental property, and this is what's going to allow us to explore a lot of things in the real numbers, or exponentiating with real numbers. We can look at exponentiation acting on top of exponentiation. If we have x to the a and then raise that to the b, then that means we've got x to the a b times, multiplied by itself b times. So this will give us a total of a times b x's. Why is that the case? Well, imagine if in each box there are 5 rocks. Well, if we've got 3 of these boxes, then it is 3 times 5. So if we've got a rocks in each box, a x's in each of these boxes, each of these x to the a's, and we have b many of them, then it must be a times b of them in total. Thus, x to the a to the b is equal to x to the a times b. We just multiply the two exponents in that case. We can also consider what happens if we have 2 different numbers each raised to the same exponent. If we have x to the a times y to the a, then we've got a many x's and a many y's. But we can also shuffle things around, right? xy is the same thing as yx. We're pretty confident in this. That's one of the cool things about working with the real numbers, is that they're commutative. They're allowed to swap their spaces. 2 times 3 is the exact same thing as 3 times 2. So x times y is the same thing as y times x, which also means that if we have xx times yy, if we feel like it, because we're allowed to commute, we're allowed to swap the locations in multiplication, then we could switch this to xy, xy, which is exactly what we do here. We take these x's and these y's and we sort of file them together. So one x here, one y here, next x here, next y here. So we'll have xy, xy, that will show up a total of a times as well. So x to the a times y to the a, if we want, we can write it as x to the xy, that quantity, all raised to the a. Now, let's try to figure out what happens when we raise a number to the 0. Our first sort of difficult question. X to the 0 equals what? So, first off, we can write x equals x anytime we want. Just definitionally, that's sort of the idea of equality. You are equal to yourself. So we can write x equals x as x to the 1 equals x to the 1, right? We can put it to an exponent of 1 because that just means it's itself just multiplied just once. It's just there by itself because there's only one of them. So there's nothing wrong with writing x equals x as x to the 1 equals x to the 1. But not only that, we know that 1 is equal to 1 plus 0, right? 1 plus 0 is just 1. So if we want, we can take this 1 right here, and we'll substitute it for 1 plus 0, and we have x to the 1 plus 0, and then we'll just sort of knock out this 1 and leave it as x, just so it's easier to read what's going on. So we've got x to the 1 plus 0 equals x. So this means we've got a 0 on the field that we can play with. By our new property, x to the a plus b equals x to the a times x to the b, sort of our most basic property, then we can break this up and we can take the 1 and separate it from the 0. So we'll have x to the 1 and x to the 0. And we'll just write x to the 1 as just x by itself, since that's what it is. So we've got x times x to the 0 equals x. Now, as long as x is not equal to 0, if x is not equal to 0, if x is equal to 0, we can't really divide by it easily. But as long as x is not equal to 0, we divide by x. We cancel out the x's on both sides since they show up on both sides. They disappear, and we're left with x to the 0 equals 1. There we go. Thus, any number, as long as it isn't 0, raised to the 0 becomes 1. So we take any number at all, we raise it to the 0, it's going to become 1. 5 to the 0 equals 1. Negative 52 to the 0 equals 1. 47 million to the 0, you guessed it, equals 1. So whatever we take, if we raise it to the 0, it becomes 1. Next, what happens when we raise something to a negative number? For ease, let's just figure out what happens with x to the negative 1. We begin similarly. X to the 1 equals x to the 1. You can't stop me from saying that just because it's the same thing on both sides. And then we can also say 1 equals 2 minus 1, right? 2 minus 1, that equals 1. So if we want, we can substitute in on this side here, and we've got x to the 2 minus 1 equals x. Now, notice we've got a negative 1 on the field. So we use that property, we break it apart, and so by our property, x to the a plus b becomes a times x to the b, x to the a times x to the b. We've got x squared times x to the negative 1. So x squared times x to the negative 1 equals x. Now, we can divide by x squared, once again, as long as x is not equal to 0. If we have that, then things get troublesome. But if we divide by x squared, the x squared goes from here over to here. And so we get x to the negative 1 equals x over x squared, right? X over x squared. And so x divided by x squared, that cancels the x on top, turns this to a 1, and we're left with equals 1 over x. So x to the negative 1 equals 1 over x. Thus, any number, as long as it isn't 0, raised to a negative flips to its reciprocal. If we have some number and we raise it to a negative, we will get that number flipped into the reciprocal format. 5 to the negative 1 equals 1 to the 5th. So what if we want to know what x to the negative a is, for any a at all? Well, x to the negative a, well, from the other work that we just did, where we know that negative 1 to the a, because it's negative 1 times a, so we can write it in that way as well. And so we've got 1 over x to the a equals 1 over x to the a. So a negative in our exponent causes it to flip to its reciprocal format, but it will still keep whatever that original exponent number was as well. So the number will go with, but the negative is a flip. So negatives flip, but this number that we're exponentiating to will still stay with it. With this idea, we can consider if we had a fraction raised to the -1. So not just a number, but a whole fraction. So x over y to the -1, well, you can't stop me from separating that into x times 1 over y. And then we can distribute that -1. Remember, xy to the a is equal to x to the a times y to the a. So that -1 will go on to both the x and to the 1 over y. So we've got x to the -1 times 1 over y to the -1. X to the -1 flips to 1 over x. 1 over y will flip to y over 1, or just y. And so we've got y over x. So negative exponents flip fractions. If we've got a negative exponent, we flip whatever it is. Whether it's a fraction or it's a number, we flip to the reciprocal. Great. We can also look at if we have powers in the numerator and the denominator with the same base. The base is just the thing that's having that exponentiation happen to it. So x is our base in almost all of these examples. So x to the a over x to the b, well, we can separate that into x to the a times 1 over x to the b, right? We've got x to the a on top, so we separate that. So x to the a times 1 over x, and that whole thing to the b, is equal to x to the a times x to the negative b, because 1 over x is equal to x to the -1. So 1 over x to the b is equal to x to the negative b. And now x to the a times x to the negative b, that combines through addition, which in this case will become subtraction. So we've got x to the a minus b. Thus, the denominator's power subtracts from the numerator's power. That's another thing that we've got out of this. Finally, what happens when we raise a number to a fraction? For ease, let's look at just x to the 1/2 first. I'll make it easier to understand. Once again, we start from the same place. X to the 1 equals x to the 1. And like usual, we want to bring 1/2 to bear. So we notice 1 equals 1/2 plus 1/2. Simple as that. So now we can substitute in. We swap this in for here, and we've got x to the 1/2 plus 1/2 equals x. Now notice, we can use our property x to the a plus b equals x to the a times x to the b, the usual property we've been using, to separate this into x to the 1/2 times x to the 1/2 equals x. We've already got a name for that. Square root, right? Square root x times square root x equals x. That's the idea behind square root. The definition of square root is some number that when you multiply it by itself, it becomes the number you took the square root of. So root x times root x is just some number that when you multiply it by itself, it becomes x. So if x to the 1/2 times x to the 1/2 is equal to x, then that must be the same thing as root x, because it does the exact same property. Itself times itself becomes x, so we already have a name for that. We call that square root. So with this property, we see that x to the 1/2 equals the square root of x. They're equivalent. We can expand this by similar logic to x to the 1 over n. So x to the 1 over n is the same thing as saying x to the 1 over n times itself, n times, is equal to x, because we've got n many 1 over n's is equal to 1. So if we combine x to the 1 over n times x to the 1 over n, we'll be adding 1 over n to itself n times, which is equal to 1. So x to the 1 over n times itself n times is equal to our x, by the same logic that we split up x to the 1/2. By definition, the nth root of a number is something that when it multiplies by itself n times, we get the original number, right? The cube root of something, the third root of something, is a number that when it multiplies by itself 3 times, we get our original number. The nth root of something is a number that when it multiplies by itself n times, we get the original number. Well, hey, look, we're multiplying by itself n times. We're getting that original number out of it, so it must be that x to the 1 over n is equal to the nth root of x. With this idea in mind, we can use any rational number that we want at all. We can have x to the a over b. We can separate that into x to the a times x to the a to the 1 over b. And since we had just had this thing here, 1 over n is the same thing as nth root. So we've got 1 over b becomes root b. So we've got the root b of x to the a, the bth root of x to the a. We're just mixing the two properties. The numerator is normal exponentiation, just multiplying by itself like we normally would expect. And then the denominator takes a root. It takes that bth root because it's 1 over b. Cool. At this point, we've got a lot of different rules, and we can see a summary. So our foremost, most fundamental rule of all is this idea right here. X to the a times x to the b equals x to the a plus b. From there, we are able to figure out all these other rules. X to the a to the b is equal to multiplying the two together. So if we've got two different exponents raised on one thing, it multiplies them together. If we've got x to the a times y to the a, we can combine that to just having x to the y, xy to 1a. X to the 0 is always equal to 1. So if you're raising to the 0th, you always come out to being a 1, as long as we're not dealing with x equal to 0, which we won't address. X to the negative a equals 1 over x to the a, right? We flip with negative exponents. If you've got a negative here, then you flip down to the bottom. If we've got a fraction with a negative, then the whole fraction flips to its reciprocal. We got y over x to the a. And we also see that x to the a divided by x to the b becomes x to the a minus b. Finally, our nth root stuff, x to the 1 over n is equal to the nth root of x. X to the a over b is equal to the bth root of x to the a, which is the same thing as the bth root of x to the a, right? Because as opposed to splitting it, we could split this as 1 over b to the a, which we'd see as the bth root of x all raised to the a, and that's where we're getting that. So two different ways of looking at it. Sometimes it'll be more convenient to have the bth root of x to the a. Other times it'd be more convenient to have the bth root of x all raised to the a. It'll depend on the specific problem. Remember, and this is I really want you to take away this idea here. If you forget any of these rules, you can figure them out from this fundamental basic idea. X to the a times x to the b equals x to the a plus b. You just have to come up with some creative way to get the thing that you're trying to figure out, whether it's roots, whether it's fractions, whether it's 0, whether it's negative numbers. You figure out some creative way to get 0, negative 1, 1 over 2, 1 over n, something like that to show up, and then you look at it and you go, oh, I see, that's what it is. And so even if you forget this in the middle of an exam, someplace where you can't go and look it up in a book, you can figure this out on your own. It's not that hard, and having worked through it and understanding how we're getting this, it's that much more likely to stick in your brain. I know it seems like a lot of rules, right? But once you start using them, you get used to using them, they'll stick in your head, and as long as you remember this one, you can ultimately get back anything that you've forgotten by accident. All right. Final idea, what if we want to raise to the irrational? So far, we've actually only discussed exponentiation using rational numbers. That's the only thing we've technically dealt with. We've got a over b for any a and b, but we haven't dealt with what if it can't be expressed as a over b, like root 2. So what if we want to raise something to an irrational number? Let's say we want to look at 3 to the root 2. Notice, if we want to, we can look at as many places of root 2 as we want, right? We can figure out that root 2 is equal to 1.41421356, and it will just keep marching on forever because it's an irrational number, so its decimal expansion goes on forever, never repeating, always changing, constantly going on forever, but we can figure out what that is. Furthermore, we know how to exponentiate to any rational number, so we can raise to any decimal, because any decimal is actually something that we can express as a rational. For example, 1.4, if we want to, we can express that as 14 divided by 10. 1.414, if we wanted to, we could express that as 1,414 divided by 1,000. Right? So we can do any of these based on all of the work that we just had. So we could do 3 to the 1.4 as 14 over 10. 3 to the 1.414 is 1,414 divided by 1,000. So we see that the work we've just done gives us a way to figure these things out. Of course, it'd be very difficult for us to do these by hand, but there are methods to do these things. We could do it by hand, but we'll leave it to the calculator since they can do it so much faster. We can use a calculator and get this done so much faster because they've already been programmed with how these methods work. So we can take these various things and see 3 to the 1.4 becomes 4.6555. 3 to the 1.414 becomes 4.7276. 3 to the 1.41421 becomes 4.7287. 3 to the 1.414213.5 becomes 4.7288. So notice, as we use more and more of these decimals, we see the exponentiation. This 3 to the root 2, we see it sort of stabilized to a single thing, right? The 4 always gets used, the 7 always gets used, the 2 always gets used, that 8 always gets used. We see that it's becoming more and more and more stable, that we're seeing more and more of these decimal places show up, and they're not going to change. They're going to stay there forever. So while we can't get the whole number all at once, right, it's going to wind up being irrational, so it's going to also have a decimal expansion that continues forever, constantly changing. But it is stabilizing to something. So we can get this idea that while we can't write it down on paper, because it would require an infinite amount of paper, the number does exist. And so we can get as many decimals as we need for whatever our use is. So we won't formally define this, but we see that irrational exponents make sense because we're stabilizing to some number. As long as we use lots and lots of decimals when we calculate it out, 3 to the lots and lots of decimals from what we're originally trying to use as our irrational number, we'll be able to get something that's a very, very close approximation to the exact number that we're trying to sort of strive towards, but won't ever be able to perfectly reach. All right, cool. Ready for some examples. Evaluate 8 over 27, all raised to the negative 2/3. So with many of these examples, there's actually going to be multiple ways that we could approach it, so I'll try to show you the various ways that you could go at it. So 8 over 27 to the negative 2/3, first thing I would do is I'd see, we've got this negative sign, so I'm going to flip and get rid of that negative. So we've got 27 over 8 to the 2/3 equals, and now we've got 2 and thirds, so I'd put the third into nth roots on both of them. So we've got the third root, the cube root of 27, cube root of 8, and so we now no longer have that dividing by 3 to worry about, but we still have the squared because we didn't get rid of it by putting anything out there. So cube root of 27, 3 times 3 times 3 is 27, so we've got 3. 2 times 2 times 2 is 8, so we've got 2. That's all raised to the 2 once again, so that's 3 squared over 2 squared. It gets distributed 9 over 4, and there's our answer. But there's also other ways we could have done this. We could have seen this as 8 over 27 to the negative 2/3, and we could have gone about this as flipping to 27 over 8 to the 2/3. Sorry. And we could then put this as 27 squared over 8 squared to the 1/3. And that's going to be kind of difficult for us to do. So we could do this with a calculator, and then we could take the cube root of 27 squared over 8 squared, and that would eventually simplify out to 9 over 4. But that'd be very difficult to do by hand, but notice that we can do the cube root of 27, we can do the cube root of 8, so this is probably the much easier way to do this. Furthermore, we could even go about this by taking this as 8 over 27, we could put this as negative 2/3 on 8, and then 27 to the negative 2/3. And then, since they're both negative, they'd flip into 27 to the 2/3, 8 to the 2/3. So we'd have 27 to the 2/3, 8 to the 2/3, and then we could once again do either this method here or this method here. At this point, I think pretty clearly this here is our best bet, the easiest way to do it, where we go through this method, because we see, hey, 8, 27, I'm going to have to deal with cube roots. 8 and 27, those are things I can easily take a cube root of, so I'm going to do cube root first, then square, and I'll also get rid of that negative as just sort of a first step. You can do these things in many different orders because the rules all work together, but you'll want to get a sense, as you work on more and more examples, you'll get a sense of, the way that will make this problem easiest is for me to go through like this. And so just sort of you'll develop an intuition about it, and even if you wind up going in a way that's not the easiest, it will still work out. It just might require using a calculator or require a little extra effort. All right, next one. Simplify x squared over z to the negative 2 times x squared y cubed z to the negative 1, all cubed, divided by y to the 8th. All right, so first thing I'd do is I would deal with the negatives once again. Usually that's easiest, so this will become z over x squared, all raised to the now positive 2, times, and let's distribute this 3, so the 3 will go onto the x squared, go onto the y cubed, go onto the z to the negative 1, so x to the 2 times 3, because we had exponentiation on exponentiation, y to the 3 times 3, z to the negative 1 times 3, all divided by y to the 8th. We can deal with this squared. We get z squared over, with that 2 also distributes, so the 2 distributes onto the top and the bottom. So x squared squared is x squared times x squared, or x to the 4th. Also x to the 2 times 2, another way of looking at it. Times, so x to the 6th, y to the 9th, z to the negative 3, all over y to the 8th. At this point, we see we can cancel out the y to the 8th. This becomes y to the 1, which we could also look at as y to the 9 minus 8, right? Because we've got 1 on top, 1 on bottom, which would also become y to the 1. So various ways to do this. Z squared times x to the 6th times, I'll move that over. So let's put all of our symbols, all of our variables, so that they are near their similar ones. So we've got x to the 6th times y to the 1, which I'll just leave as y, times z squared times z to the negative 3, all over x to the 4th. And that's all we've got on the bottom at this point. So we see we've got z squared, see we've got z to the negative 3, so that'll cancel out and we'll get negative 1, because negative 3 plus 2, z to the 2 times z to the negative 3, so z squared times z to the negative 3, they combine through addition because they're both just multiplying each other. So we've got z to the 2 minus 3, which becomes z to the negative 1, which is how we get what we have right here. X to the 6th divided by x to the 4th, that'll cancel out all but 2 of these, which we could also see as x to the 6th minus 4, which equals x squared. So we've got x squared times y times z to the negative 1, and since z to the negative 1 is 1 over z, we can write this as x squared y all over z. Once again, like our first example, there's other things that we could have done at various points. If we wanted to, we could have broken off here, and we probably could have written this as z squared over x to the 4th on our next step times x to the 6th, y to the 9th, and then z to the negative 3 over y to the 8th. At this point, we see z to the negative 3, so we could move that over, and we could go x to the 6th over x to the 4th, times y to the 9th over y to the 8th, times z squared, and since we had z to the negative 3, we could also write that as z cubed. At this point, we've got x to the 6 minus 4 times y to the 9 minus 8 times z to the 2 minus 3. So we've got x to the 2 times y to the 1 times z to the negative 1, which also becomes x squared y over z. Or if we wanted to, we could also just go, hey, we've got 9 y's on top, 8 y's on the bottom, so all of them will cancel on the bottom, and 1 will be left on the top. Similar things with the x's and the z's. So there's a variety of ways to look at these things once you get into this. And once again, it's about developing an intuition and just doing it a bunch of times. And also just be comfortable in the fact that whatever way you choose, as long as you follow the rules, they'll all wind up working out eventually. Third example, simplify the nth root of 5n times 5 to the 3n, all raised to the 2n, divided by 5 to the 6n squared. All right, so this is a great one to show 2 different ways to approach this. Let's leave that nth root intact in our first run. So nth root, 5n times 5 to the 3n, well, 5n times 5 to the 3n, because they're multiplying, we'll go through addition, 5 to the n plus 5 to the 3n. So we've got 5 to the 4n, all raised to the 2n, over still 5 to the 6n squared. Let's expand that radical a bit so we see the whole thing. Equals, still got that nth root 5 to the 4n times 2n, because it was exponentiation on exponentiation. So 4n on 2n over 5 6n squared equals nth root of 5 to the 8. 4 times 2 is 8. N times n is n squared over 5 to the 6n squared. Now at this point you might be tempted to cancel out our n squareds, but that would be improper because it's not like canceling 3 over 3 where we can cancel both of them because they're dividing. It's different because it's about how many times they show up. So we have to use the rule that we have, which is when we've got a fraction with something on top, something on the bottom, it subtracts if they've got the same thing on the bottom. They're both 5s, so they can use this rule. So it's still the nth root, so it's going to be 5 to the 8n squared minus 6n squared. So those are common terms. So that becomes 8n squared minus 6n squared. 8 minus 6 is 2, but it still has n squared. So 5 to the 2n squared. Nth root is just the same thing as saying 1 over n. So 5 to the 2n squared times 1 over n equals 5 to the 2n. Great. Alternative way we could have done this, though, is taking something to the nth root is 1 over n, whenever we do it. So 5n times 5 to the 3n, once again, that'll be 5 to the 4n, because they add together. And that's all raised to the 2n over 5 to the 6n squared. Now, everything, because it was radical of the whole thing, so it's got to be that the whole thing is raised to the 1 over n. Now, we can distribute. We can distribute this, and we can say that's 5 to the 4n. Let's leave that as 2n times 1 over n over 5 to the 6n squared times 1 over n, because this 1 over n will get applied to the top and to the bottom of our fraction. 5 to the 4n, well, these n's cancel out. This 1 over n cancels out the squared, leaves the n, so we've got 5 to the 4n squared over 5 to the 6n. 5 to the 4n times 2, because it was exponentiation on exponentiation, still 5 to the 6n, equals 5 to the 8n over 5 to the 6n equals 5 to the 8n minus 6n, which, hey, that equals 5 to the 2n just as well. Great. So, two different ways of doing it, very different approaches, going through the inside or going from the outside in or inside out, but they both wind up giving us the exact same answers. It's one of the great things about all these rules. They all work together. There's no like preference of one rule versus the other. So sometimes it generates various different paths that we could go, but you'll develop an intuition, and once again, they all will wind up working out. So just make sure you practice this stuff on your own, and you'll develop a sense for how this works, and it'll get faster and faster the more you practice it. All right, another example. F of x equals 7, x to the 2/3 minus 2, g of x equals x to the 6/5. Give f composed with g of x and simplify. Now remember, first thing when we talked about function composition, f of g of x is almost always the way we want to switch to writing this. F acting on g acting on x. So what is g of x? G of x is x to the 6/5. So x to the 6/5. F of x to the 6/5. So now it's not about the x, it's about where does the box of input go into our formula for that function. So f of box equals 7 box to the 2/3 minus 2. So in this case, our box is x to the 6/5. So we've got 7 times box x to the 6/5, and then that box raised to the 2/3 minus 2, because that's what our whole function said before. So 7 times x to the 6/5, because it's exponentiation on exponentiation, it's multiplication. 2/3 minus 2, 7 times x. 6/5 times 2/3, we notice 6 can be broken into 3 times 2, so that knocks out this 3 and this 3, and we're left with 2 times 2 on the top, so that's 4 divided by 5 minus 2. So 7 times x to the 4/5 minus 2 is what f composed with g comes out to be. Final example, let x be a number such that 7 to the x equals 3/5. What is 49 to the x? Now at first you might see a problem like this and it's completely confusing because you have no idea what to do. But notice we've got 7 here, we've got 49 here. So there's going to be some sort of clever trick connecting the fact that 49 has something to do with 7, right? How is 49 related to 7? 49 is equal to 7 squared, right? So there's this connection between 49 and 7. So we can use that. We can now apply that, and we can go 49 to the x. Well, we know that 49 is equal to 7 squared, so we can just substitute that out. So 49, put it in parentheses, to the x is the same thing as 7 squared to the x, right? Nothing you can do to just stop substitution like that. So 7 squared to the x. So that means 7 to the 2 times x, but we could also write that as 7 to the x times 2, which we could then write as 7 to the x all raised to the 2, which would be, hey, we know what 7 to the x is. It's 3/5. So we've got 3/5 all raised to the 2, which means we've got 9 over 25, because we square the 3 and we square the 5. 3/5 squared means that the square will go onto the 3, go onto the 5. All right, pretty cool stuff, exponents. They're really, really powerful. It's important to get a good grasp of just working with them, though. The only way that you'll be able to get really comfortable with them is doing some practice. Just make sure that you do some practice on exponentiation using exponents of various types. But once you get in a bit of practice, you'll get used to it. They're skills that sort of stick with you. And as long as you stay with this x to the a times x to the b equals x to the a plus b, as long as you stay with that idea, you can figure out everything else if you get in a situation where you forget one of the rules. All right, we'll see you at educator.com later. Bye.